Hello everyone, I'm Changfang. Nice to meet you. I come from Nanjing University of Science and Technology, and my presentation title is Structural Mechanics of Auxetic Steels Prepared by Carbon Fiber Reinforced Epoxy Resin Laminate. This is my biography. It shows my education background, academic experience, and research interest. My research fields are mechanics of fiber reinforced composite materials and structures. Next, I will present a recent investigation published in Composite Structures, which mainly focuses on the negative Poisson's reduced structures, also called auxetic steels, made of carbon fiber composite. Including background, introduction, preparation process, experimental methods, results and discussions, conclusion and outlook. The first is the introduction part, which mainly shares the application background of carbon fiber composites, the concept of negative Poisson's reduced effect, and the negative Poisson's reduced structure. Here, the abbreviation of negative Poisson's reduced is NPR, and the abbreviation of negative Poisson's reduced effect is called NPRE. Besides, the abbreviation of carbon fiber reinforced plastics composite is named as CFRP. CFRP is currently the advanced fiber composite that most widely used because it has very excellent specific strength, specific stiffness, and specific energy absorption, which makes it popular in the structural design of aircraft, automobiles, ships, rockets, and other transportation tools. Here, specific energy absorption can be named as SEA. Actually, it can be found that these products achieve weight reduction by replacing metal materials with CFRP, because the lighter the transport means, the lower the energy consumption and the longer the running distance. Most important, CFRP has the function of absorbing energy during the collision event, because the high SEA can reduce the damage to the driver or occupant due to impact overload. However, the SEA produced by structures with different configurations is also different, which is related to its mechanical process. Some structures absorb energy through deformation, while others through materials failure. The progressive failure of CFRP is a very classic case of energy absorption by material failure. The plastic folding under axial compression of metal thin-walled tubes is also a classic case of energy absorption by structural deformation of load. Some metal NPR structures also realize energy absorption through plastic deformation. What's more, some studies combine the two energy absorption methods to improve the SEA, such as the honeycomb structures filled with aluminum 2M. Compared with the NPR structures, the energy absorption of the traditional structures is still not good enough because the NPR structure can realize the abnormal phenomenon of compression, contraction, or tension expansion. Therefore, it can produce the indentation resistance to greatly improve the mechanical properties and energy absorption. These pictures are NPR structures or materials, and it can be found that the NPRE of compression contraction is indeed realized. Besides, the NPRE can also contribute to anti-shear, anti-fracture, and other effects, but we now focus on the compression properties. There have been some reports on composite NPR structures. The types of NPR structures are classic arrow structures, such as the reentrant structures, star-shaped structures, and others. These NPR structures are mainly prepared by 3D printing, namely the additive manufacturing technology, and some of are assembled by designing detachable components. Some studies have shown that the strength of CFRP prepared by 3D printing is still not good as that of prepared by high-temperature hot freezing method. For the 3D printing, the CFRP, its products have shortcomings such as uneven materials, uneven fibers, and voids or defects like these figures. Besides, Its price is high and the product size is limited. For the assembled product, its assembly process is complicated and it will have discontinuous mechanical behavior at the inert position. Therefore, it is a challenge to prepare the CFRP NPR structures by high-temperature hot pressing. To this end, we try to prepare a re-enchant NPR structure and carried out a series of studies. The preparation section mainly describes the technological process of CFRP NPR structure. The preparation process includes preparing the unidirectional preparage, preparing the combined model, laying the preparage on the model, completing the hot pressing in the tank, demodeling and machine. Meanwhile, the temperature and pressure curves make this figure. And this is the specific preparation process, that is, the traditional high-temperature hot pressing modeling method. I think we can skip it first. The experimental section describes the types of experiments and structures. First is about the loading and date acquisition method. The experimental process is quasi-static compressive loading with the stream rate of 0.02 per second. For some structures, a full-field stream measurement and analysis system was introduced to obtain deformation and calculate the Poisson's ratio. Then, the dimensions and the directions of the structures are defined like this figure. The structure types include open series structures of CN1, CN2, and CN3 based on the half-steel structures, and the closed series structures of CN4, CN5, and CN6 based on the full-steel structures. Next comes to the most important part, the experimental results and discussions. Firstly, the open cell structures of CN1, CN2, and CN3. These structures are cemented with high-strength epoxy resin, whose model is 3M-DP490. Their mechanical behaviors have linear and non-linear characteristics, and the non-linearity is more obvious with the increasing number of half cells. The deformation and failure of the structures include compression contraction, arrows coming to contract, sidewall cracking and delamination, and then fracture, structural collapse, and there is a Z-shape inner hull seal of CN3. Of note, they all achieved a negative Poisson's ratio effect, namely the NPRE. Secondly, the hull seal structure of CN4. This structure is the key research object. So it was loaded in 3 directions defined above. For the direction 1, compression, the structure has 2 linear characteristics before failure, which is caused by different load-bearing positions. At the beginning, the loading is located on the arrow rod. After a small displacement, the left and right side walls come into load until the side walls break, which corresponds to the string counter on the right. In the first linear stage, the NPRE is realized. After that, the side walls buckled and deformed outward, manifesting as a positive Poisson's ratio effect instead of the NPRE. The failure conditions were similar to the previous structures. However, arrow cracking and debonding occurred. And for the direction to compression of CN4, we set up a control group that bonded with high-strength epoxy resin to discuss the effect of bonding interface strength. In contrast, the elastic mechanical behavior of the 2 structures is similar, and the deformation and failure are also similar. However, there are some differences in the mechanical behavior and deformation after failure. The structure of adhesive CN4 having to has greater stiffness and strength, and there is no debonding phenomenon at the adhesion interface. After compaction, it shows the Z-shape configuration, which is similar to the closed structure of CN3. The results of direction 3 compression are different from the others. The mechanical behavior of CN4-3 has a load plateau, which is due to the fiber layer bearing load vertically to need the progressive failure. The final result of compression failure shows the phenomenon of bulges and barrels of load. This progressive failure is the comprehensive result of fiber and matrixal tensile compression and shearing, cracking and delamination, and is also accompanied by debonding and shear fracture on the adhesion interface. Thirdly, for the two-cell structure of CN5, its compressive mechanical properties mainly include the minor stage and the plateau stage. Here, the plateau stage corresponds to the compressive buckling deformation, which is resulted by the increase of structure's mass. The deformation and failure of CN5 structure are similar to the CN4 in the direction 2. But the debonding of the adhesion interface is dominant due to buckling deformation. Finally, for the three-cell structure of CN6, whose compressive mechanical behavior is similar to that of CN5, but the plateau stage is missing a needle. Deformation and failure are the same as CN5. When the structure is missing, buckling deformation will occur, which can avoid several cell wall cracking, delamination, and fracture. But this is not friendly to energy absorption because of the short compression displacement. According to the full-field strain analysis system, by calculation, except for CN4 noted in direction 3, the NPRE of all design structures was achieved. However, CN5 and CN6 have larger negative Poisson's ratios, which may be caused by their lower stiffness. The initial load peak, stiffness, and SEA of CN4 noted in the direction 3 are all the largest, which is the contribution of progressive failure. It can be seen that the material failure energy absorption of CFRP NPR structures is greater than the deformation failure energy absorption. Furthermore, it is worth noting that the trigger load for progressive failure is very large, which is about 20 times the deformation failure load. By summarizing the experimental results of CFRP NPR structures, the following conclusions can be drawn. Number 1. Mechanical behavior includes linear elasticity, non-linear yielding, load plateau, and failure stage. Number 2. Negative Poisson's ratio effect can be achieved except for loading in the direction 3. Number 3. The strength of the adhesion first will affect the mechanical behavior. Number 4. In addition to loading in the direction 3, the failure types include adhesion first cracking and debonding, sidewall cracking, delamination and fracture, and concave angle fracture. Number 5. Progressive failure has the highest energy absorption and ACA, but also has the highest initial load peak and stiffness. Number 6. The overall appearance of the progressive failure in the direction 3 is bulges and barrels. Number 7. The mechanical behavior of the multi-cell structure is similar to that of the single-cell structure, but the multi-cell structure will suffer from buckling instability. The above is the work that has been carried out so far. However, this is only a small part of the mechanical properties on the CFRP NPR structures. In the Outlook section, we present the next research plan. The future research plan mainly includes the later multi-cell structure and its sandwich structure to discover the multi-cell coupling effect. The filling structure, which allows for the superposition of energy absorption from material and structure. The dynamic and impact mechanical behavior. As energy absorbing structure is commonly used in high-speed draws. The finite element simulation to obtain the mechanical characteristics of other more conditions. The structural optimization analysis, such as wall thickness, concave angle, and sidewall length. They have an adverse influence on the NPRE and energy absorption. Lastly, I would like to thank my supervisors at to authors and affiliations. I hope my presentation will interest you. I'm very pleased to get a collaboration with you. Looking forward to your later. That's all.